Okay, so the last talk of the short course will be given by Professor Jim Fuller. And so we're going to transition from talking about microscopic properties to very macroscopic properties. So now we're going to hear about linking tidal, rotational, and orbital evolution. Jim Fuller is a professor here, an assistant professor here at Caltech. And he comes at the tides question from a theoretical astrophysics perspective and has worked on tides in stellar systems, but has also recently done some great work on the Saturn system and the orbital migration of the Saturnian satellites. So we may be hearing something about that today. Here you go, Jim.
Yeah, thank you, Catherine. Thanks for having me. Yeah, so we just heard from Christine about some of the physics on the shortest time scales, shortest length scales, how that affects tidal dissipation in satellites. Now we're going to transition to the opposite limit, largest length scales, longest time scales of order gigayears is what I'm going to focus on, and how that all relates. So I guess for the next week we'll be trying to sort of piece those two pictures together. So I want to start today with a pop quiz. What is the energy source for Enceladus's geysers, or I guess we could say for Iowa's volcanoes? Is it the rotational energy of the giant planet hosts? Is it orbital energy, elastic energy in the tidal deformation, or thermal energy in some sort of ocean? So, okay, I won't make you reveal your answer to everybody. But of course, it's a trick question. The answer is all of the above. If we really want to understand volcanoes, geysers, and things like that, we really need to piece together all these different pieces of the puzzle and see how the energy flows all the way from the planet to the geysers and microbes that are getting shot out into space. So yeah, a lot of this talk I'm going to focus on the Saturn system, but actually a lot of the physics and dynamics I'm going to talk about are equally applicable to, say, the Galilean satellites. The basic idea is we have some big planet, dominates the mass and energy of the system, surrounded by a bunch of puny little satellites that, despite being puny, do raise a little bit of a tidal bulge on the planet. That does cause some migration of these satellites. They start interacting with each other. They start getting caught in resonances. So in Saturn, for instance, Mimas and Tethys are in a 4-2 inclination resonance. Enceladus and Dione are in a 2-to-1 resonance, eccentricity resonance. Rhea out here by itself, not interacting with anybody. And then Titan further out is basically on its own as well. I guess it's in a resonance with Hyperion, but the point is this whole dance is going to be driven by the migration of these moons that's due to tidal dissipation inside of the giant planet. If we don't understand the tidal dissipation in the planet, we're not going to understand the timescales or energetics of any of the rest of the system. So that's an important question. It's a very similar picture for Jupiter. We just have only 4 major moons involved, and in this case we have Io, Europa, and Ganymede, each in 2-to-1 resonances with each other. Okay, so the long-term evolution looks something like this. We start with moons fairly close to the planet, so in Saturn's case, maybe just outside of the rings. Those moons migrate outwards. In this case, I colored, say, Mimas and Tethys. I colored their orbits red at the point where maybe they lock into a 2-to-1 resonance. At some other point in time, you might get another pair of moons locked into resonance, and the system will proceed. And this whole picture will last for probably gigayears, and it can be very complex. There can be many different resonances encountered, and so piecing together the long-term evolution can be quite complicated, but that's the basic idea. So this is all driven, like I said, by tidal dissipation in the planet, which is really what I've worked on. So I just want to go through some basics. So the idea is we have some planet which would have been spherical, or, well, giant planets are rotationally distorted, but they would have had some equilibrium structure if not for this perturbing tidal potential of a moon. That tidal potential scales like basically just a potential of the planet times the mass ratio of the moon divided by the planet's mass. Now in giant planets, this mass ratio tends to be very small, less than 1 in 1,000. Times the radius of the planet divided by the semi-major axis cubed. Again, this number, radius over semi-major axis, tends to be a small number of order 1 over several for giant planets cubed. So this tidal potential is very small compared to the planet's potential. So this is a very small effect. The typical tidal displacement you get goes something like that tidal potential divided by the planet's gravity. And so that, again, will scale basically with m prime over m times r over a cubed, very small number. And the energy in the tidal bulge is something like the acceleration provided by that potential times the displacement over which you displace material. And that scales now with m prime over m squared, r over a to the 6. So the kinds of energies we're talking about are very tiny as far as the global energy budget of the planet. But over 5 gigayear timescales, even this kind of small tidal distortion, when dissipated, can have an effect. So I think we already heard from Francis a little bit about tidal queues. So the basic idea, the way people usually parameterize tides in planets, is by this ignorance factor Q, which goes something like 1 over Q is basically proportional to the angle between the direction of the tidal bulge and the direction connecting the centers of masses of the planet and the moon. Okay, so calculating, if we know this angle, we can calculate the tidal torque, and we can calculate the evolution of the system, but actually calculating this angle is really tricky. That depends on the dissipative properties of the giant planet. Now, giant planets usually are not composed of grains, so actually, I think in many ways, understanding their quality factors is even more difficult than understanding quality factors of terrestrial planets and moons, because we can't just rely on some sort of frictional effects inside of the solid material. We have to rely on some sort of fluid dissipation mechanism inside of the gas and fluid inside of the giant planet. But the basic idea is we have some effective tidal bulge that's displaced. Because giant planets rotate faster than their moons, their tidal bulge actually doesn't lag the planet, it really goes in front of the moon. And so that provides a torque on the moon. The moon gains angular momentum and spirals away from the planet over time. Of course, it's the same picture for the Earth and the moon. The Earth rotates much faster than the moon. So over time, the moon is accelerated away from the Earth. Okay, so none of this is new. But I think a lot of the times people think of all this in terms of some tidal Q of a planet, and they assume that this tidal Q is some fundamental constant written on a stone tablet, and we just have to figure out what that constant is, and then we'll be able to solve all the giant planet and moon evolution problems. I would say this Q is actually probably a dynamic property. I'll discuss how it might be affected by the long-term evolution of the system. And instead of thinking about a tidal Q, I like to think in terms of a tidal migration timescale, which is basically just some orbital energy divided by some energy dissipation rate inside of the planet. So if we can figure out what that energy dissipation rate is, we can figure out the effective tidal Q and understand how moons evolve. Okay, so the simplest picture that people discuss, and the oldest picture associated with tidal dissipation, is that of equilibrium tides. So the idea here is you have your tidally distorted giant planet, and because it's getting squished back and forth, there's some shear basically associated with the velocity inside of the planet. Because there's shear, friction can act on that shear and can dissipate some of the kinetic energy associated with those motions. So the problem is that friction, so if we just compute, say, some viscosity of gaseous material inside of giant planets, it's totally negligible. It's orders of magnitude too small to account for any substantial migration of the moons within the lifetime of the solar system. So usually what people appeal to is some sort of turbulent viscosity in the convective envelope. That the effective turbulent viscosity will scale something like a typical velocity of a convective element times a typical length scale of those convective motions. And the other thing people appeal to is viscoelasticity inside the solid cores of giant planets. So if those solid cores are there, they can produce viscoelastic response that produces dissipation, just like we heard from Christine. The problem is for giant planets, you need a pretty large core and you need it to be solid for this to be important. I think that's probably evidence that those kinds of solid cores don't exist. So the effective tidal dissipation rate that you get from this kind of equilibrium tidal process will scale something like this effective viscosity, usually associated with some sort of turbulence, divided by, this is just length scale of this shear, which is r squared, times the energy contained in this tidal bulge. That's kind of the energy scale we're working with here. So, like I said, people have been computing this for a long time. It's hard to get this kind of energy dissipation rate to produce much migration of the moons. So what has been studied a lot in recent years are dynamical tides. Dynamical tides are some sort of tidal response, usually in the fluid parts of giant planets, that are usually composed of waves excited by the gravitational forcing of the companion. The kinds of waves that are most important in the fluid envelopes of giant planets are inertial waves. Inertial waves are waves that can usually propagate in convective regions. Their restoring force is basically a Coriolis force. The other kinds of waves that can be excited are gravity waves. So if you have some part of your planet that is stably stratified, buoyancy waves can propagate in those parts of the planet, and those can be excited by the tidal forcing of the moon. And those waves will also be dissipated by various frictional processes, and that energy dissipation rate can actually be quite important. The reason that dynamical tides can be very important, even though the amount of energy stored in this dynamical tidal response is typically quite a bit smaller than the amount of energy stored in the equilibrium tidal bulge. But the length scales of these waves are typically much shorter. They have much higher wave numbers. So like if you look at this, this is a calculation of inertial waves. In this case, inertial waves are focused onto these attractors. They have very small widths. That means they have large shear and large wave numbers across these bands. And so the effective wave numbers on which something like turbulent viscosity could act are much larger. So that means even though you have less energy in the dynamical tidal bulge, you can actually have a larger energy dissipation rate. So in many cases, dynamical tides may actually dominate the energy dissipation. So some work that's been done on this is a nice plot from Ogilvy and Lin, 2004. This is a calculation of an energy dissipation rate due to inertial waves inside of a giant planet. In this case, this giant planet, I believe, has a solid core in this model. But the energy dissipation you're seeing here is not coming from the solid region of the planet. It's coming from inertial waves that are trapped between the surface of the planet and the solid core of the planet. And you'll see that this energy dissipation rate is an extremely sensitive function of the tidal forcing frequency. That's omega here. So you'll see that basically we only get these large peaks where energy dissipation rate is large in between the frequency of -2 and 2. So this is normalized to the rotation rate. That's saying that basically these inertial waves only exist if their frequency is less than twice the spin frequency. And that's because they're restored by Coriolis forces. These peaks are associated with more or less resonances. They're associated with frequencies at which you can basically have a wave path that follows a closed path here. And that means all the energy is concentrated in these basically regions of the planet with very small length scale. So that's how you get a lot of dissipation by inertial waves. And so there's no Q associated with a planet undergoing tidal dissipation by this mechanism. Instead, the energy dissipation rate can vary by orders of magnitude over very small ranges in frequency. So when people study this kind of tidal response, they'll often talk about some sort of frequency average dissipation rate. And that frequency average dissipation rate might be what you expect to correspond to roughly the tidal Q associated with this kind of dissipation mechanism. What I'll say in a few minutes is that I think actually, if you think about actually how the system evolves through these resonances, then the behavior you get can be quite a bit different. So this is something I've worked on for Saturn. So this is a plot from one of my papers where I didn't compute the inertial waves. I just computed an energy dissipation rate or a tidal migration timescale due to resonances with gravity modes that might propagate inside of a stably stratified region in Saturn's core. And what we see on this plot is that at most semi-major axes, so semi-major axis is in this case a proxy for tidal forcing frequency. At most tidal forcing frequencies, the tidal migration timescale is very long, and you essentially get no migration. But at very narrow and specific frequencies associated with the resonances of gravity modes, we can have much shorter tidal migration timescales. And that's because at these frequencies, basically the moon will resonantly excite the dynamical tide, composed of G modes in this case. Those G modes will reach large amplitude, and so the energy dissipated by those G modes can be quite large. So another way of thinking of that, so the first plot was in terms of tidal timescale. We can also think of that process in terms of an effective tidal Q. So there might be some effective tidal Q due to, say, turbulent dissipation of the equilibrium tide, but there may be many frequencies where there's a much lower effective tidal Q associated with resonances with gravity modes or with inertial waves or some component of the dynamical tide. Okay, so a lot of this work has been prompted by recent measurements by Valerie in the back row of effective tidal Qs for some of Saturn's moons. So these are the results from his paper a few years ago of the effective tidal Qs he's measured for Enceladus, Tethys, and Dione. They're of order 2,000. So in a minute I'll explain why even this measurement was very surprising. This is about a factor of 10 lower Q than people expected. And what's most interesting to me is that the effective tidal Q associated with Rhea was a factor of several smaller than that associated with the other moons, which means that even Rhea, according to these measurements, has experienced substantial tidal migration over the lifetime of the system. But I think what's most important here is that the tidal Qs of different moons appear to be very different. And so that's the clear signature of dynamical tides acting, at least in Saturn. Okay, so I want to discuss an idea I've worked on called resonance locking, where the idea is that tidal dissipation can be produced by these resonances in our dynamical tidal dissipation spectrum, but that moons can actually get caught in these resonances. And so the effective tidal Q can actually be much smaller than some sort of frequency averaged Q. And that relies on planets getting caught in these resonances, which I'll explain in a bit. But the basic idea is that because the structures of giant planets evolve slowly over time, for instance, Saturn evolves on a thermal timescale, which is basically Saturn's potential energy or gravitational energy divided by the luminosity that's radiating. That corresponds to a timescale of something like 100 gigayears. So we might expect the internal structure to evolve on timescales around 100 gigayears or maybe of order 10 gigayears, comparable to or longer than the age of the solar system. So the structures of planets evolve, and that means that all the frequencies associated with all these resonances with inertial waves or gravity waves, all those frequencies will evolve on these very long time scales. So that means they're not just constant. Even if a moon wasn't tidally migrating at all, these resonant frequencies would sweep past a moon, and moons would pass through these resonances even in the absence of any migration of the moons. And what happens when one of these resonances sweeps by a moon can be very interesting. Okay, so I'm going to walk you through the dynamics in this plot. So this is just a simple model where I've calculated a tidal dissipation timescale, in this case due to a gravity mode inside of Saturn, as a function of semi-major axis, and I've zoomed in around one of those resonances. So we have basically a very small semi-major axis scale here. So this is the resonance with the G mode. And we can imagine that this resonance is moving one direction or the other as the planet's evolving. So let's imagine the resonance is moving to the right. That would correspond to the resonant frequency slowly increasing with time. So it turns out that there's a point just outside of the resonance, denoted by this red circle, where the migration time scale is equal to the time scale at which this resonant frequency is moving, which is denoted by this green line. Okay, so if we put a moon right at this location, this is a stable equilibrium point where a moon can just surf this resonance outwards. Okay, so you can think about it this way. If I put the moon here, it will migrate at the same rate that this peak is moving and stay there. If I displace the moon inwards from that point, the tidal migration timescale will become shorter, so the moon will migrate back out and catch back up to this equilibrium point. If I displace the moon a little bit outwards, its tidal migration timescale will increase, the moon will stop migrating very fast, and this resonant peak will catch back up with the moon. So it's a stable point, and if a moon gets caught at this resonance lock, we expect it to just migrate outwards at the same time scale that this resonant frequency is migrating, which, like I said, can be set by the evolution of the planet. So in this picture, we'd expect moons, when they're caught in resonance locks, to migrate outwards on planetary evolution timescales, regardless of basically the semi-major axis or mass of the moon. So the picture I like to say is that these moons like to surf these resonances outwards. So you can imagine it's just like surfing a wave in from shore. There's some equilibrium point on the wave where basically you're riding down on the wave at the same rate that it's propagating forward. So you can get caught in that point and surf the wave inwards. And so moons can do a similar thing potentially with these resonances. And in this case, in the case of giant planets, surf these resonances outwards. So in this picture, this tidal migration rate is basically just set by some time scale T alpha, corresponding to the rate at which the resonant frequency is evolving. And that will, like I said, scale with some planetary evolution time scale. So the tidal migration time scale in this picture goes like basically that resonant frequency evolution time scale times some function, in this case basically orbital frequency of the moon divided by the difference between the orbital frequency and the planet's spin frequency. So there could be, for a constant T alpha, there's some small dependence of the migration rate on, say, the moon's orbital frequency, but it's a fairly weak dependence compared to something like a constant tidal Q model. And in this picture, the effective Q that you get during a resonance lock has this nasty equation, but the point is Q is not some quantity determined by the planet. It's basically just determined, again, by this evolution time scale of the modes. And so this Q can change with time, and it can change for moons at different locations and different semi-major axes. So again, I said, if we come back to these measurements, the green bars are the effective Q measured by Valerie, and the blue boxes are predictions from this resonance locking model. And they've been tuned basically so that there's some evolution timescale, about 50 gig years. For that kind of evolution timescale of Saturn's internal structure, you can match Rhea's migration rate quite accurately. And the agreement is not so good with Tethys and Dione. There are big error bars here. I think these measurements are still evolving a little, but we have to be careful with these moons because they're caught in resonances with Mimas and Enceladus. And so that means measuring all these effects and exactly defining what we mean by tidal Qs, if it's the tidal Q of Tethys or the tidal Q of Tethys being pushed by Mimas. We have to be a little bit careful. But I think the way I like to look at this picture is the effective tidal migration timescales measured by Valerie. The Qs are different, but the migration timescales are all consistent with a migration timescale of order 10 gigayears for all the moons. And again, that's basically what you expect from something like a resonance locking picture. So in terms of the long-term evolution of the system, the resonance locking or constant tidal Q have pretty different predictions for the prior evolution of the system. So this is a plot taken from a recent paper by Nakajima. If you basically take the measured migration rates of the moons and evolve them backwards in time, that corresponds, and you assume Q is constant, then you basically get that all the moons about a gigayear ago had to have started inside of the planet. Okay, so if we assume a constant tidal Q, the currently measured migration rates are inconsistent with the moons having formed at the same time as the giant planets, at least for Saturn. So there's two options to get around this problem. One is that the moons really did form a few gigayears after Saturn. Some work has been done on that possibility. The other is that Q is not actually, well, I guess another possibility is that the measurements are somehow wrong, that Q is much larger, and in that case, the moons would follow evolutions along these dashed lines. So then they would be consistent with having formed at the same time as Saturn. I think that's unlikely. The third possibility is that Q is not constant and that the migration history is actually different. So if you make a similar plot based on the resonance locking criterion, then the effective Q actually changes. It's basically this tidal migration timescale that's constant. The effective Q would have had to have been larger in the past. And so again, these solid lines are the paths moons would take as we go backwards in time according to a constant tidal Q. The dashed lines are the paths they would take according to basically a resonance locking picture where it's the tidal migration timescale that's a constant, or roughly constant. And so that, in that case, the fast current migration of the moons would be consistent with them actually having formed at the same time as Saturn. In this case, because they're actually accelerating, they're actually migrating faster now than they were in the past. They're migrating at about the same rate, but the effective tidal Q is actually lower now than it was in the past. Okay, so regardless of how the migration works, if moons cross resonances with each other during their evolution, of course, this is going to cause a lot of the interesting effects that we're interested in this workshop. And that tends to happen at mean motion resonances, specifically J equals 1 or 2 mean motion resonances, where we basically have the orbital frequency of two moons, 1 and 2, related by a ratio of integers. At these resonances, the moons exchange angular momentum, and so the eccentricity and inclination of the moons is increased. Now, really these mean motion resonances are quite complicated because they're split by the non-spherical potential of the planet. So what that means is that the precession, the vertical and radial precession frequencies become different. And so that means the resonances become split according to eccentricity type resonances, where we basically, what comes into play now is basically epicyclic oscillation frequencies, either in the radial or z direction come into play, so that each one of those mean motion resonances gets split into several eccentricity and inclination type resonances. So here's a nice plot from one of Francis Nimmo's papers from a few years ago, looking at all the different resonances that moons may have crossed in the past. This is again for Saturn. And so we see this is, I think, using a constant tidal Q of, do you remember, Francis? 18,000, yeah, which is what people often quote for Mimas. And so in this picture, these moons have all crossed potentially many resonances with each other. And if you zoom in on one of these resonances, so like this resonance between Dione and Enceladus, it's actually split into many different components And currently, that system is trapped in one of those eccentricity type resonances. But the point is, all this history, it's undoubtedly complex, but the whole history of which resonances are crossed is going to depend on exactly how these moons have migrated as a function of time, whether these lines slope downwards like this, or in a resonance locking picture slope more constant like that. And so that means the long-term evolution of the system is really dependent on how this tidal migration changes as a function of time. Now, of course, if moons become eccentric, they get distorted as they change their distance away from the planet. That causes tidal heating, which I think Francis talked about earlier. But we can actually relate that tidal heating rate. We can get a really rough estimate of it really simply by assuming that moons have reached some equilibrium between eccentricity pumping and eccentricity damping by tidal heating. So the tidal heating rate for low eccentricity will just scale with eccentricity squared. And so there's some equilibrium for a moon getting pushed into a mean motion resonance with an outer moon. There's some equilibrium eccentricity at which point the eccentricity pumping provided by the resonance is matched by the eccentricity damping. We can calculate that equilibrium eccentricity, and it's going to scale with the tidal quality factor of the moon divided by the tidal quality factor of the planet, and in addition to some other factors. And at this equilibrium eccentricity, there's basically a stable tidal heating rate, which doesn't depend on what this equilibrium eccentricity is. It's basically just given by the energy, the orbital energy of the outer moon, divided by the tidal migration timescale. This is the tidal heating rate that you need in order to basically have two moons migrate outwards and maintain a mean motion resonance and maintain very low eccentricities, and have basically energy and angular momentum being added only to the inner moon by tides. So the point is that this tidal heating rate, to order of magnitude, is just set by orbital energy divided by some tidal migration timescale. So if we can figure out what this tidal migration timescale is, we can calculate the typical tidal heating rate. So if you just plug in numbers, say for Enceladus, we'd estimate a tidal heating rate of something like 50 gigawatts, and that's within a factor of a few of the measured heat flow coming out of Enceladus. So it's a pretty good rough estimate. Now, I just want to say a quick bit about some of these other theories. So like I said, based on the current apparent fast migration rates of moons, one possibility for explaining them is that tidal Q is more or less constant, but moons have actually formed more recently than 4.5 gig years ago. And so one idea that's been put forth for Saturn is that Saturn used to have more massive set of rings. As those rings expand, they form moonlets at the outer edge. Those moonlets migrate outwards due to torques associated with the rings. The moonlets crash into each other, make larger moonlets, and those moonlets keep building into smaller mid-sized moons. And so this is an example of a calculation done by Charnos et al. 2011, where they try to calculate this, this sequence of moon creations and moon mergers over gig-year timescales. And they typically, it's some stochastic process, but they do find some sort of chain of moonlets with some mass spectrum, and you tend to get larger moons further away from the planet. And when you compare this sort of a typical outcome of one of their simulations, it is similar to the mass spectrum and orbital distances of Saturn's mid-sized moons. So that is another potential way of creating the moons. Okay, so to conclude, I just want to say that nothing about the standard lore has really changed. I mean, we know tides drive moons outward, they encounter resonances, there's heating and things like that. But I think some of the ideas we could talk about during this workshop are some of the new ideas that might change how this picture works over long time scales. And so one of those ideas is that there's not some constant tidal Q, that actually the tidal Q varies with time. And that's the expectation from dynamical tides. The expectation from resonance locking is that moon migration timescales are comparable to planetary evolution timescales, And this could apply to many moons. It might apply to moons as far inwards as Mimas, or moons as far outwards as, say, Titan or Callisto. And so we might actually get a lot of tidal evolution, even for moons that we had suspected, that we had assumed before didn't actually undergo any tidal migration. So again, that could happen for outer moons especially. And finally, I think it's possible that there's been much more rapid tidal migration of certain moons than people have expected in the past. In some cases, there may have been ring-driven migration for Saturn's inner moons. And I think the last possibility to consider is that maybe some of the moons are really quite young, and that would, of course, have important implications for the dynamics and tidal heating of these very recently formed moons. Okay, that's everything. Thanks.